Okay, I hope the PPT is visible. So in the previous class, what we discussed was about the Harris corner detector. So we saw how we can detect a region with a corner. So you can identify regions as regions which are flat or homogeneous. That is, you do not have any edges or corners, or you can have regions with edges, and you can have regions with the presence of a corner, one or more corners. And for detecting such patches, to detect whether it has a corner or not, we saw how we can try to get the data distribution and see and fit an ellipse and see how the region can be identified with respect to the eigenvalues, or with respect to the ellipse parameters. And the type of corner detection technique that we saw was the Harris corner detector. And next, what we're going to learn is the KLT tracking method. So in the KLT tracking method, we make use of the Harris corner detector, and that is why it was important to learn that first. Now, for object tracking, we saw different types of tracking techniques. So first, we saw the tracking by object detection, where a detection algorithm was used to detect the objects present in different frames, and then the tracking was accordingly identified, or the trajectory was accordingly identified. Then the other main category of tracking method is the tracking by matching, where we try to match different patches, the image patches between different successive frames, and we try to track the motion of the particular object. And under that comes the matching by summary representation, where instead of taking the image patches as such and doing a pixel to pixel comparison as we do in SST, what we do here is, for the summary representation, we take a patch and use the histogram representation, and then try to see how the histogram matches, and with that we'll try to track. And another type which we were learning about was the optical flow trackers. Now we'll be learning about Klt tracking method. So in the Klt tracking method, we will be going, by a step-by-step procedure on how this is done. But overall, what is done is, here we try to formulate this tracking method as a registration problem. Okay, in the sense, what we do is we take different patches and we try to register the two patches, or what we assume is that, let's say you have an initial frame. So from the initial frame, if I just try drawing that, let's say I have an initial frame here and I have a particular patch here, right? So in the subsequent frame, in the next frame that I have here, let's say the patch is present somewhere over here. So you have the same object, okay, but it kind of, let's say it is translated by, it is a translation operation, let's say. So what we do here is we try to find the alignment, or we try to find out what is the transformation that has happened between the patch. And by formulating that as a registration problem or as an alignment problem, where we try to find out what is the transformation that has occurred, okay, we try to track the motion or the movement of a particular object. Okay, so the KLT tracking method, the full form of that is Kennedy Lucas Tomasi tracker. So we just call it as the KLT tracker. Now we'll see how, what is the step-by-step procedure for that. Okay, so in the KLT algorithm, now there are various versions of the KLT algorithm, but in the original KLT algorithm, this is the different steps by which it is done. So in the first step, what we do is we detect the Harris corners which are present in the first frame. So in the very first frame, which is present in the video, we try to use the Harris corner detector and we try to detect the corners. Okay, so and that will act as the key points for us, right? Now what we do is we can calculate what is the motion, okay, of that particular object. Now that when you say motion of the particular object, or of the particular corner points, It can be a translation motion. It can be a Euclidean motion where Euclidean, or you can also call it as a rigid motion where it can be translation as well as a rotation, or it can be an affine motion. So the motion can be, it can be any kind of transformation. It can be translation or rigid or affine or projective or so on, right? So what we do here is whatever we is a type of transformation, we will try to compute that particular motion for each of the Harris corners, okay, between successive image frames that you have, right? Then the next step is we try to link the motion vectors in the successive frames in order to get a track for each of the Harris points. So there may be multiple Harris points which are present in that image or in the particular object of interest for us or domain of interest for us, right? And for each of the Harris points, after finding what is the motion, we try to link all that together to form the trajectory, right? And then what we do is, in order to ensure that we have tracked sufficient number of points, okay, just to ensure that we have not lost track of any point, what we do is we can apply the Harris corner detector at every, let's say, intervals of frames, like it can be every 10th frame or let's say every 15th frame or so on. So why we do this is, see, from this itself, we do get a trajectory, but there is a chance that, let's say, some points has been misdetected or some points has not been detected at some frames. So when that happens, what happens is that that motion of that particular, corner point, okay, is lost, maybe lost at some point or at some frame due to some errors, okay, or let's say there are new points that are being identified or so on. So just to ensure that there is no error or deviation from the actual trajectory that we are trying to track, what we do is after every, let's say, intervals of frames of 10th or 14th, 15th frames and so on, we again apply the Harris corner detection algorithm to, introduce or to ensure that all the sufficient number of points are used for tracking. Okay, so this is just to reduce the error. So we'll just see one example also on how this happens. And then, so what we are doing is, so you have these new points, you have the old points, so we keep tracking and this goes on. So each time the video is being played, you have the Harris corner detection algorithm, which detects the corner points. It is being tracked throughout for a set of successive frames. And again, you have the detection algorithm used. So there may be new points, there may be old points recovered or so on. Again, this motion has been linked with the successive frames, and this keeps on repeating. Okay, so this is how the simple or the original KLT algorithm works. Okay, so here, if you look at this video, what we'll see is, you can see that the corners have been detected, okay, by the Klt tracker. And you can, these yellow points that you see here are the new points which have been detected at every, when you're repeating the Harris corner detector at every interval of frame. Okay, so that is, let's say, 10th or 15th frame or so on. Okay, and by this way, by detecting these corners and by trying to track the motion of these corners, what happens is overall you're trying to, you are able to detect what is the trajectory of the whole object as a whole as such. Okay, so in one particular object itself, you might have many corner points and you're trying to track all the corner points together. Okay, and this is just a practical example of that. Okay, so as I said earlier, what we are doing is we are basically trying to align two different patches, right? So if you have a patch and a successive patch, okay, patch in the sense in the whole image, we are taking just the corner or a patch or a small region where you have the corner points, right? So given that patch, and if in the successive frame, again you have another patch, right? So given these two patches, as I said before, what we are doing is we are trying to find out what is the transformation that has occurred to this patch in order to obtain the patch in the next frame. Okay, or what is the alignment that has occurred between the two patches. That is what the KLT algorithm is doing. Now, how do you exactly estimate this alignment, or how do you find out what is the kind of transformation, or how do we evaluate that, okay, or estimate that? That is what we're going to see next. Okay, so here again, one thing you have to remember is in the KLT algorithm, it is basically what we are doing is actually tracking. Okay, so the basic objective what we are doing is tracking the object itself, but all that we are doing is this tracking problem, we are just trying to reformulate that as a registering problem. So by trying to find out how or what is the transformation that has occurred with between two patches, okay, that transformation is kind of interpreted as a tracking. Like for example, let's say if the transformation that has occurred between the two patches is something as simple as a translation operation. If it's just a translation operation, what that means is it has either moved in the towards the x direction or the y direction, vertically or horizontally, it has just moved, right? So if it is as simple as that, while saying that, okay, so this is a transformation that has occurred, what we're trying to say is that, okay, while tracking, yes, it has moved in so and so direction, right? So just to take a very simple example. So basically it's a tracking problem, but what we're doing is we are just reformulating that as a registering problem. And in this registering problem, what we are doing is we are trying to find out what is the transformation between two patches, and two patches in the sense a patch in the current frame with a similar patch in the next frame, okay, or in the consecutive frame. And because it is the image patches, it would be 2D transformations that we are considering. So the formulas that is associated with the transformation methods would be corresponding 2D formulas. You will have only two coordinates, x and y coordinates. And these are the formulas for the different types of transformations, and this is something which we have already seen earlier. So in the case of translation, you can say in the x dash new coordinate, all that you have is you have a vector or a parameter that expresses how much it has moved in the x direction, and in y dash you have another parameter that expresses how much it has moved in the y direction, right? So you can, it's as simple as writing x dash is equal to x plus b1, y dash is equal to y plus b2, and b1 and b2 are the parameters that you have, or the unknowns that you have for the translation transformation. So if it is a translation transformation that has occurred, then by determining what are these unknowns or what are these parameters, we'll be able to estimate how exactly the transformation has occurred. Similarly, let's say if it's a rigid transformation. For a rigid transformation, rigid includes both rotation as well as translation. Okay, so when there is a rotation, theta parameter is involved, and for translation you have b1 and b2, and the corresponding formulas are x cos theta minus y sin theta plus b1, and x sin theta plus y cos theta plus b2. So these are something, these formulas have already been discussed earlier. We have also discussed that in matrix form also, right? Then you have affine transformation. So for the affine transformation, the different parameters are a1, a2, b1, a3, a4, b2, and for the projective transformation, you have a1, a2, b1, c1, c2, and a3, a4, b2, c1, c2. So just remember that for the affine transformation and the projective transformation here, as we have learned in the first few classes, okay, we have the homogeneous form representation in this case. Okay. Okay. Now what we'll see is, let us see how we can express all these transformations as vector valued functions. Okay, so vector valued functions in the sense we are just trying to represent it in a vector form. Okay, and the vector valued function is given by w bracket w for warping, that we'll see later. Okay, that term and the concept we'll see later. So w, because warping in the sense it could be, it's actually a type of aligned. What you're saying is if you have a particular image and you have a patch over here, right, and in the next frame you have the patch over here, let's say, and we are saying that there is some kind of a transformation that has occurred in this patch to get this, right? So you can say that if we know what is the transformation metrics or the transformation parameters, you can warp, that particular patch to, this given resultant patch, or in order to get the resultant patch. That is, if we apply this particular transformation to the original patch over here, or the first patch in the current frame over here, we get the warped image. Okay, so for that we represent this W here. And for representing each of these transformations as a vector valued function, what we do is we can just write this as capital W X semicolon P. So here these values, now X basically represents this X dash and Y dash parameters. So basically that is the coordinates, right? And this P stands for the parameters. Okay, so these parameters will change with the type of transformation that you are dealing with. Like for example, let's say it is a translation. Let's say the transformation that has occurred is a simple translation operation. So if it is a translation transformation which has occurred, I can write the formula as x dash is equal to x plus b1, y dash is equal to y plus b1, right? So if I'm rewriting that in the form of a vector valued function, how I can write is wx semicolon p is equal to x plus b1 comma y plus b2. So basically this is my x1 here, okay, and this one is my sorry, not x1, sorry, it's x dash here, and this one is my y dash, right? And the parameters that I have here is b1 and b2. Okay, now if I'm taking a rigid transformation, let's say, then I have, if I look at the formulas, you'll see that I have the parameters as theta, b1 and b2. Okay, and how I can write the vector valued function is shown over here. So again, here this one is my, till here is my x dash, and here what I have, this is my y dash. Okay, and similarly for affine transformation, the formulas are given by this. So here a1x plus a2y plus b1 and a3x plus a4y plus b2. Okay, so this is the normalized case over here. So how I can write the parameters here is, I can write it as a1x plus a2y plus b1, this being my x dash and this being my y dash. Okay, so this is how I can represent it as a vector valued function. And as I said earlier, the parameters here would differ. So in the case of rigid transformation, the parameters that I have is theta, b1 and b2. In the case of affine transformation, the different parameters that I have is basically the unknowns are a1, a2, b1 and a3, a4, b2. Okay, now before we go with how to deal with the vector valued functions, we'll just see some definitions of derivatives and gradients. Okay, so let's say I have a function given, okay, which is f of x, which is given by f of x. Now, if I can, in order to find the derivative, what I can do is I can just express it as f dash x is equal to df by dx, right, where x is a scalar. Now, let's say I have a function f which is dependent on different variables, right? I have x1, x2 till xn. It's a function of different variables x1 to xn. So in order to find the derivative, or basically the gradient, what I can do is I can write del f of this particular function is given by, what I can do is I can find the partial derivative of the function with respect to each of the variables. Okay, so this is when you have different variables here, right? So I can express this as dou f by dou x1, dou f by dou x2, etc. till dou f by dou xn. Let's say if you have n dimensions. So that means, for example, if I'm taking the case of an image, in the case of an image, my the function which I have would be, I have two components there. I have f of x and y. So because I have two coordinates. So in that case, when I'm trying to calculate the gradient, right? So what I find is I basically try to find out what is dou f by dou x and dou f by dou y. right? So for different dimensions that you have or different coordinates that you have, this is how you can generally represent a function with different variables. So what you do is basically try to calculate the partial derivative of the function with respect to each of those variables. Now, when you come to a vector valued function, so vector valued function, we have just discussed earlier that we can represent the transformation methods with respect to w, x, semicolon, p, right? And what is the equation that would change depending upon what is the type of transformation that we are using, right? So for such vector valued functions, let's see how we can find the derivative, right? So when I'm writing a vector valued function in general, I can write it as f of x1, x2, x3, etc. Okay, it will have different components here. So if I see this is one component, that is, I can write it as a function f1, which is also a function of all these variables x1 to xn. And I can write another component of this, which is f2, which is also a function of all these variables, etc. Let's say I have m such functions or components which are functions of all these variables x1 to xn. So the different components that I have is f1, f2, let's say till fm, right? So if I want to find the derivative of such a vector valued function as shown over here, what I need to do is I can just calculate the Jacobian over here. Okay, so by definition, how we write the Jacobian is I write j of f, that is the Jacobian of this particular vector valued function, is given by dou f1 by dou x1. This one would be dou f1 by dou x2, etc. Dou f1 by dou xn. Okay, and here it would be dou f2 by dou x1, dou f2 by dou x2, etc. And the last one would be dou fm by dou x1 until the end dou fm by dou xn. So what this means is, now what I'm doing is along this row, if you observe along this row, what you see is the in this whole row you're trying to find the partial derivative of the function f1 throughout, okay, with each of the different variables. So for this particular column it's x1, for this particular column it's x2, etc. For this particular column it's xn. Okay, so you're trying to find the partial derivative of f1 with respect to x1, that would be your first element. Trying to find the partial derivative of f1 with respect to x2, that's going to be a second element, and so on. So the last element would be trying to find the partial derivative of f1 with respect to xn, and that would be here. Similarly, if I'm looking at the second row, this would be with respect to the second function, and last one would be with respect to the last function, okay, fm. And so this is row wise. Now if I'm trying to look at column wise, what I see is, okay, in this column I'm trying to find what is the partial derivative of f1 with respect to x1. Here it is partial derivative of f2 with respect to x1. And here it is the last element in this column is dou fm with respect to dou x1. That means all the functions, I'm trying to find the partial derivative of all of these functions with respect to the same variable, which is x1. Right. So similarly, column wise, if I'm saying, this would be for all functions with respect to x2, partial derivative of all functions with respect to xn. Okay, so this is how you can write the Jacobian of a particular function, and we use this Jacobian in order to find the derivative of a vector valued function. Okay, so as I said earlier, we are trying to formulate these different transformations. We are trying to write the different transformation equations that we have in the form of a vector valued function, right? So we are writing it as w x semicolon p. So now if you have this vector valued function, as I said earlier, in order to find the derivative, you just need to find the Jacobian, right? So let's see what would be the matrices when you're trying to find here, okay? So w xp, we know that is represented by x plus b1, y plus b2, right? That is my vector valued function corresponding to the translation operation. So if I'm trying to find out the Jacobian of this particular vector valued function, what I write is, as I said earlier, okay, I have the first function over here. Okay, so the first function f1 would be here, the second function f2 would be here. Okay, and with respect to what is the parameter that we are using, okay, that parameter. So here you have two parameters b1 and b2, therefore I'm using b1 parameter here and b2 parameter here, right, for calculating the partial derivative. So here the partial derivative would be with respect to dou by dou b1. Okay, and the function that I have is the first function that you see here, right? It is x plus b1, so I can write it as x plus b1. This is going to be my first term. Now the second term will be dou f1 with respect to b2, so it's going to be dou by dou b2 of the function is x plus b1. So similarly, I can write here the function as dou of y plus b2 divided by dou b1, and here this is going to be dou of y plus b2 divided by dou b2. Okay, so this is how I write the Jacobian. Now, when I evaluate this, when I try to find the partial derivative of this, what I get would be, in this term you have this b1, so you have 1. Here you do not have any b2 terms, so it would be 0. Here again you do not have any b1 term, so it's going to be 0. Here you have a b2 term, so it's going to be 1. So finally what you're getting is, when you're calculating the Jacobian, finally what you're getting is this particular matrix. Okay, dou w by dou p is given by 1 0 0 1 for the translation transformation. Okay, now similarly you can find out for the rigid. So if you are taking a rigid transformation, as I said earlier, rigid transformation involves both rotation as well as translation operation. So in this case, wxp is given by x cos theta minus y sin theta plus b1, and x sin theta plus y cos theta plus b2. And as I said earlier, in order to find the Jacobian of this, what I need to do is I just have to find the partial derivatives of each of the functions. So you have this is let's say this one that we have here is the function 1. Here what we have is function 2. So with respect to f1 and f2, and now you have different parameters here, right? So I can take the different parameters b1, b2 and theta, and then try to find out dou f1 by dou b1, dou f1 by dou b2, and so on. So after finding this, you'll see that the answer that you'll get would be 1 0 minus x sine theta minus y cos theta, and 0 1 and x cos theta minus y sine theta. That would be your Jacobian, or the derivative for the vector valued function for a rigid transformation. Similarly, for the next one, that is affine transformation, also you can follow the same thing. Okay, and the parameters that you'll be using would be b1 and b2, and a1, a2, a3 and a4, right? And then after solving that, the answer that you'll get would be 1 0 x y 0 0 0 1 0 0 xy. So you can just try solving by yourself and you'll get that. So what you need to remember here is, when you have a vector valued function, or when you're trying to represent a transformation as a vector valued function, okay, and then trying to find the gradient of that, how we can find the gradient is by using the Jacobian function, and this is how you calculate the matrices corresponding to that. So as you see here, in this case, this is going to be a 2 cross 3 matrix. Okay, in this case, you have 6 different columns here, so it's going to be a 2 cross 6 matrix for the affine transformation. Okay, now that we have discussed about how we can express the transformations in the form of a vector valued function and how we can find the gradient, now we'll see how exactly do we do this alignment. Okay, so let's say this is the image that you have, right? And this green color box is the image patch that we are considering. Within that image, this is the patch that we are trying to track, or we are trying to capture the motion of, right? And as I said earlier, how we track over here is by converting this as a registration problem. So what we do is we try to find what is the alignment of the transformation that has happened of this patch with respect to the patch in the next consecutive frame. So what we do here is, now if you look at these two images, okay, now this t of x is what you call as the template. Okay, so you have a template of the patch which is given by t of x, and here I of w of xp is basically the warped image. Okay, now w of xp, as you know, that is any 2D transformation. It can be translation, or it can be a rigid transformation, or it can be a affine transformation. And then you have I. Okay, so I of this means what you're doing is it is representing a warped image, in the sense the patch which is obtained after applying this particular transformation to the original patch. Okay, so basically this frame is what you see in the second second frame. Okay, so let's say this is a first frame and you have a particular patch over here, and by applying a transformation you get another patch here, right? So this particular transformation is given by wxp here, and this is my image. So when I'm trying to apply this transformation to this particular image, I get this warped image over here, right? So this particular warped image, okay, is represented by this notation, which is given by I of w xp. Okay, so now in order to find out how or what is the alignment, or how exactly, or what is the transformation that has occurred, we are trying to reformulate this problem as a minimization problem. Okay, so what we are saying is I can try to find out what is the SSD, or the sum of squared distance, or difference between these two different patches. Okay, and for that I need to find out the parameter p which minimizes that function. Okay, so that is what I write is, I can write it as the warped image minus the template, right? And that one I'm squaring it, and then I'm summing it over different values of x, okay, or the coordinates that you have. And by doing this, this is basically the SSD, representation, of similar way by which you calculate the SSD, or sum of square difference. Okay, and here in this case, what we are doing is we are trying to find out that between the warped image and the template. Okay, and we are trying to find out what exactly are the values of these parameters for which this particular function is minimized. Okay, so that is how we are trying to formulate the problem. So by finding out p or the parameters, once you know the parameters, then that means you know what is the transformation that has occurred, right? Now if you have this ideal set of parameters, what happens is the sum of square difference that you have here would ideally tend to 0. Okay, so what we do is, we need a as low value as possible for SSD. So that is basically what you mean by minimizing the problem. Now, this parameter p, that would change with what is the type of transformation that we are using. Like for example, we saw that for p, in the case of transformation, translation, what happens is the values of p, or the parameters p, are b1 and b2. In the case of a rigid registration or transformation, you have it as b1, b2, and theta, and so on. Okay, so these values are what are exactly the parameters that would change depending upon what is the type of transformation that we are assuming. And let us assume that we know what is the initial estimate of p, right? So if we know what is the initial estimate of p, then this problem changes to trying to find out delta p, in the sense what we can say is that if we know what is the initial set of parameters, okay, if by finding out what is the change in the parameters delta p, okay, change in the parameters in the sense change in the parameters to get the corresponding patch in the next frame. Okay, so in that case I can represent it in this way too, right? That is, I can write, instead of p, I can just write it as p plus delta p, where I'm assuming that I do have an estimate of p, and all that I need to find out is what is the change in the parameters that has occurred. So this is also the same minimization formula that is used, but just represented in a different form. Okay, so next what you can do it, now that you have this particular minimization expression, okay, I can use Taylor series expansion, okay, on the warped image. Okay, so when I use Taylor series expansion on the warped image, this is what I get. So how I can write it is, I can write it as I of, because we are taking the warped image, I can write it as I of wx p plus delta p. Okay, this one I'm trying to use the Taylor series expansion. So I can write this as equal to I of w of x p. Okay, that is my initial warped image, and delta I dou w by dou p into delta p. Okay, so I'll get this expression, and what I do is I can just replace this part, okay, by this equation over here. So what I get would be this one. Okay, so here I'm just replacing this by the Taylor series expansion of the first order expansion, and I get this. Now here, this dou w, okay, so before that we have this delta I over here, right? So this del I is basically my gradient, right? My image gradient. I stands for the image. This is my image gradient, and how I can represent it is by ix and iy, which means that this is the gradient along the x direction and this is the gradient along the y direction. So that's going to be my del I. Then I have dou w by dou p. So this dou w by dou p is nothing but the Jacobian function, right? So this Jacobian, as I said, it would vary depending upon what is the type of transformation that we are assuming, or what is the type of parameters that we are assuming. This particular value would change. Okay, and basically this is the Jacobian, or Jacobian in the sense we are trying to find the derivative of the different vector valued functions which represent the transformations. Then what we have is delta p. Here we have the delta p, which is the quantity that needs to be determined. Okay, and t of x, as you know, that is the template, and w xp is the warped image. Okay, so what this means is, now when you're implementing this particular formula, this is the unknown that you have, right? So what we do is we calculate all the other quantities, okay, and then we find out what is the value of delta p at which the function is minimized. Okay. Now, in order to find out this delta p such that this is minimized, the function is minimized, what we can do is we can just differentiate the function with respect to delta p and equate it to 0, right? So by doing that, by doing all the steps and simplifying, what we get would be this equation over here. I'll get delta p is equal to h inverse 2 sigma delta I dou w by dou p the whole transpose tx minus iw xp. Okay, and this h inverse is basically, it stands for sigma del I dou w by dou p transpose and delta I dou w by dou p, right? Now this H inverse, we'll see what is this H inverse in the coming slide. Okay, so what you need to remember is that the delta P on solving or trying to minimize this, okay, the value of delta P that you get would be given by this expression. And then what we do is we try to find out each of these quantities and then try to determine the value of delta P. We'll see the step-by-step procedure in one of the later slides. Okay, so as an example, let us just assume that the translation that has occurred is the transformation that has occurred is a translation operation. So if it is a translation operation, I know that the Jacobian dou w by dou p is given by 1001. We've already seen that, right? And delta I, that is equal to ix and iy, which is basically the gradient. So I can calculate this H inverse, okay, by substituting in this particular formula. So when I substitute in this expression for the Jacobian as well as the gradient of the image, what I get would be this equation, okay. That is, I get H inverse is equal to sigma. Here what I have is dou I by dou x. That is, I'm trying to find the partial derivative of the image with respect to x, okay. I'm taking the double derivative over here, right? Then here I'm trying to differentiate or trying to take the partial derivative derivative of the image with respect to x into the partial derivative of the image with respect to y. Same way you have this term too, and here this is the double derivative of the image with respect to y. So if you observe this equation, okay, this equation is nothing but what we have already studied in the previous class, which is a Harris corner detector. This is the expression for a Harris corner detector. Okay, so if we are assuming that the transformation that has occurred for a patch between two consecutive frames is a translation operation, then inverse Hessian matrix, okay, becomes just it's nothing but a Harris corner detector. Okay, it's as good as just using a Harris corner detector. Now that is the case of a translation transformation, but when you are using different other transformations, then the particular Jacobian matrix would change, and you'll get different values for that. But if it is a simple translation operation, what we see is that the H inverse matrix that you get is nothing but a Harris corner detector. So if you are trying to summarize the original Klt algorithm, this is the equation that you have determined in order to find out delta P, right? So for finding delta P, we already saw that what we need is the H inverse, okay? And we need delta I dou W by dou P, right? And so basically you need the gradient of the image, you need to find the Jacobian, and that is required for finding H inverse too. And you have the template minus the warped image, right? So once you have all these quantities or all these values, measured or estimated, you can find out what is delta P. So let's see how exactly the Klt algorithm works, or what exactly does it do by a step-by-step procedure, okay? So the first step that you have is you're trying to warp I with WXP. And that is, let's say we already have a previous estimate of P, right? And so we know what is the type of transformation which has to be applied, right? So we assume that we do have a previous estimate of P, and we know what is the transformation, and we apply that particular transformation on the image I. Okay, so by doing that, what I get would be basically the warped image. I would get what is IWXP. I'll get the warped image. Then what I can do is, so once I get this, I can subtract this from the template. Okay, so that would be my second step, where I subtract I from T. Then I can compute the gradient. Next, I can compute this gradient of the image, that would be delta I. Then the next step would be I can compute the Jacobian dou W by dou P, this particular term over here. Now I can multiply these two together to get this term, okay? And this is nothing but by multiplying the gradient with the derivative of the derivative of the the transformation with respect to the parameters here, right? So by doing that, what I'm trying to do is I'm actually doing a steepest descent, okay? In the sense, I'm trying to find out what is the direction, or what is the position at which the value of P keeps decreasing, right? Then next step is I compute what is the H inverse matrix, okay? So H inverse matrix, we just use the previous formula that was discussed, and then so once we have all these different parameters determined, I just multiply all these together, okay? So that will be the steepest descent along with the error function. Now, after calculating the steepest descent with the error function together, okay, what I get would be finally the delta P. So this delta P is basically the parameters, the updation of the parameter, or what is the change in the parameters, okay, to be made, right? So what the next step would be, or the final step would be updating the parameters of P. Whatever estimate that you initially had, that would be updated with respect to delta P. So this is how the original algorithm of the KLT works. Okay, so once you know the formula, you can easily identify what are the steps here. Now, here, it all works. It works perfectly fine. But there is a problem with the original KLT algorithm in the computational steps involved. okay, or the processing time which is involved. Now, one thing if you can observe here is when you're trying to update this delta p over here, okay, what we do is we are also trying to update this wxp, okay, because the value of p also changes, and hence we are trying to update the image also, right? So by updating the image, what happens is each time, that is each time this occurs where the updating of a parameter p occurs, the value of I, or the value in the sense the image I also changes accordingly, and therefore the gradient, finding the gradient of this also changes. That means for every pair of consecutive frames that we are considering, right, because we are taking consecutive frames over here in order to find out what is the warping that has occurred, right? So for every pair of consecutive frames, what happens is you need to keep calculating what is delta I, okay, because it is dependent upon the warping. It is basically the warped image that you have, and therefore you need to find out what is the gradient I here, okay. So each time, because this can be calculated, there can, there is an improvement that have been introduced by another author on the basic KLT algorithm in order to, reduce the computation steps or computation processing time which is involved. And what that author did was that he brought about a change in this particular step over here, where instead of calculating the gradient of the warped image, what the author did is that he has calculated the gradient of the template, okay, and the formula has been slightly rearranged, okay, in order to reduce the computation steps, and we'll see how that is done. Anyway, the result would be the same, where you're finding delta p is the same, but all that is done is a slight change in the formula, as well as a slight change in the computation of the gradient, okay, but it goes a long way in order to reduce the computational time which was involved. So we'll see that also, which is the improved KLT algorithm, and it's also called as the Klt Bergen et al. So Bergen is the author who had introduced this particular concept to the original KLT algorithm, okay, and this is an improved method. So in this improved method, what happens is, as I said earlier, we make a slight change or improvement in the formula that you're using, okay. So what we're doing here is, instead of in the previous formula, if you see in this previous formula, you're calculating the difference that you're calculating over here is t of x minus I of w of xp. That means I'm subtracting the warped image from the template, right? And when I'm using this here, I have to find out the gradient of I, or the gradient of the warped image. So since the warped image changes with every frame, or each time you're applying the transformation, the warped image changes, and therefore you need to keep recomputing the gradient over here. So what the improved algorithm does is, or what has been introduced by Bergen et al. Is, they have reformulated this in this form. That is, they just interchange these terms here. That means they try to subtract the template from the warped image. And so if we are reformulating it in this way, what we have here is, we, instead of calculating the gradient of the warped image, here we calculate the gradient of the template. Now, what difference it makes is, template means it would always be the original image that you have, right? So let's say you have this image and this is the template. The template does not change, it's fixed, okay? So what that means is, once you have an initial template for a particular image frame, right? Throughout the whole video sequence, we can use this particular template itself. The template doesn't change. Only the warped image or patch keeps changing, because each time the transformation is different, so therefore the warped image keeps changing. And but here for the template, since you can find the template using just the initial frame itself, what happens is, this template image does not keep changing. So since the template is fixed for all the image frames that happens in the video sequence, since we can keep it that way, what happens is, when you're trying to calculate the gradient of the template, you just need to calculate it once. Okay, you need not keep calculating it again and again. Okay, because the template remains the same. So by introducing this one step over here, this slight change over here, there has been a great reduction in the computation time. Okay, which has been taken in the original KLT algorithm. So yeah, so this is about the improved KLT Bergen et al. Algorithm. Okay, and this is a pictorial representation of the same algorithm that we have, that is the improved algorithm. So let's say this is the original image, just summarizing the same thing. Okay, it's just that instead of the formula, okay, they have just given a pictorial representation which shows how exactly it works step by step. So let's say you have an original image and you have this original patch over here, and it can be represented by I of x. Then from this we can calculate what is the warped image as well as the template. So it is given by I of wxp here, and it is the template is given by t of x. Now once you have t of x in the improved formula, what is done is from t of x you can calculate the gradients here, right? So the gradient is calculated, you have along the x direction as well as the y direction, and the Jacobian dou w by dou p is also calculated. So once you have the gradient information and the Jacobian together, these can be used to calculate the steepest descent here. Okay, so all that you're doing is multiplying these two, and then you have these different frames, just a pictorial representation which shows that. Then you calculate the H inverse matrix, okay, and using the same parameters, that is delta t as well as the Jacobian. And once you have all these different parameters together, everything could be multiplied together in order to find the estimate for delta p according to the formula or the equation. Now, once you have this delta p, right? Delta p is basically by how much it has to, the original set of initial set of parameters have to be updated, right? So once you have delta p, you update the parameters, okay, and accordingly the warp parameters also changes. So because it's depending on p plus delta p, so therefore you get a new warped image, okay. So this is how the algorithm works. Okay, do you have any doubts till now? Okay. So what we'll do is we'll go to the next type of tracking method. Let me see. I'll just share that again. Okay, fine. I hope the second PPT is visible. So here we just go with a new tracking method over here. Okay, so as I said earlier, we have been studying about different tracking algorithms. The first tracking algorithm being tracking using detection, where you have detectors built to identify a particular object, and or you're building a specific object detector, you're applying it to different frames and then trying to detect the object tracking or the object motion. Then we saw tracking by matching, where you have image patches and you do a pixel to pixel kind of matching there, or you have the summary representation where you use histograms. Then you have the KLT algorithm where let's say if it's a translation operation, all that you do is kind of use a Harris corner detector in order to find out the corners and then try to warp that. So in the case of KLT algorithm, this particular tracking object tracking is reformulated in the form of a registration problem. And so what is done is you have an initial frame and you have an initial patch of the image or of the object of interest. And what you're trying to do is for the next consecutive frame, you're trying to see how exactly the transformation has occurred. Okay. And in order to find the transformation, we saw how what is the formula that we use. So basically we consider a template for the first image frame, and you have a particular transformation. We assume that a particular transformation has been applied. So on applying the transformation on the original image, you get the warped image. And what you're trying to do is you're trying to find out what exactly is the transformation that has occurred. And in order to find out how the alignment has occurred, what we do is we formulate that as a minimization problem. That is, we try to find out what is the delta p values, that is the change in the parameters that has occurred between two different frames. And by formulating that, okay, that is by finding out that delta p, you are able to update the warped image. Okay, so by that what we are doing is we are trying to register that, and you are trying to find the transformation, and by finding the transformation we know what is the change that has occurred in that particular image patch between consecutive frames. Okay, so that was another way by which the tracking could be done. Now, in this technique, which is tracking linear dynamic models with Kalman filters, this is again another concept of object tracking. Okay, that is, here also we are trying to track a particular object, but what we are assuming here is that we are assuming that we already know, we have a dynamic model of that particular object that we are trying to track. In the sense, we know the dynamic model in the sense we are assuming that we have some assumption, some prior information regarding how the motion of the object would be. Okay, and with respect to that a priori information or the prior knowledge regarding the motion of the object, we incorporate that, okay, into this particular tracking algorithm. Okay, and we make use of Kalman filters. We'll come to that also, how we make use of Kalman filters. And we assume only the linear cases, that also we'll see. Okay, so what you have to remember here is that in this particular type of tracking algorithm that we are going to discuss, that is tracking linear dynamic models with Kalman filters, what is done is we make use of, or we assume that we know what is the motion of the object. Okay, and we assume that with respect to some previous observations that we have made for the particular object. And once we have this dynamics known, or we have the dynamic model for the object under consideration, we use that information in order to track that particular object. So the details we'll see in the coming slides. So before we move on to the details of the tracking, just to familiarize with two terms which you have already familiarized earlier. One is the term state, and the other one is the term measurements. Measurements are basically the observations. So what state means is what we are assuming is that every moving object will have a particular state. Okay, and this state keeps changing at each frame of the video sequence. Okay, and what we're trying to do is we're trying to basically try to measure this particular change in the state, right? And the state, it may be something that can be directly observed, it may not be something that can be directly observed. Okay, and some examples of the state is, the state could be position, or it could be position and velocity, it could be position, velocity and acceleration, or so on. Okay, so we can consider, or we can for depending upon the type of object or the type of video sequence that we are considering, we can consider any one of these states over here. And by considering the state, what we're doing is like, for example, if it's a position, what we do is we try to find out what is the change in position in every frame. Okay, now if it is velocity, we try to find out what is the change in velocity in each frame, and so on, right? Now, what do you mean by measurement is, so as I said, for each consecutive frame, so successive frames, the state of the object keeps changing, right? So this change in state would give us measurements, right? So when you're trying to measure out these changes in the state, that is what you call as measurements. Okay, and when you take these measurements, sometimes it may be corrupted by noise. Okay, you might have some kind of things crept in. Okay, so therefore we'll see that how that could be dealt with. Anyway, so what measurements that we are observing, that is called as observation. So you can use measurements and observations intervariably here. All that it means is that we are trying to observe or measure what is the changes in the state of the object, and the state could be position or velocity or acceleration, okay, depending upon what is the type of problem or what is the type of situation or video sequence that we are or object that we are trying to consider. Okay, so the terms has to be familiar. And another term that you have is the dynamics, that is the information of how the state changes with time. So what we are assuming is that when you're doing this tracking algorithm with respect to tracking with linear dynamic models, dynamics means it is the information on how the object state changes with respect to time. So if you know if you have a model, or if you know some prior information of how this object state changes with time, that can be incorporated into the tracking algorithm to predict how it will change next. Okay, so that is how that will work. It's basically trying to predict how it would change over a period of time if you already know what is the dynamic model. Okay, so now, so as I said here, what we are trying to do is the main aim over here is to maintain an accurate representation of the posterior on object state given observations and a dynamical model. What that means is, what we are trying to do is we are trying to find out a particular representation of the object state. Okay, and let's say we know what are the observations over a period of time, and we know the dynamical model, that means how the object changes with respect to time. If we have that information, prior information, as well as if you have the observations over a period of time, that can be used in order to find out what is the current change in the object state, or what is the current status or current if it is position, let's say current position of the object in the current frame, or if it's velocity, what is the velocity in the current frame, and so on. Okay, like for example, let's say we are assuming that we have an object and it is moving at a constant velocity, let's say, or let's say it is moving with a constant acceleration. So we can, if we know that if it's moving with a constant velocity, we can incorporate that information or that different types of motion information, okay, in the tracking algorithm, and therefore it would help to give you a robust a tracking algorithm, right? So what we're doing here is basically we are trying to incorporate the prior information about the motion of the object. So that's what we call as a dynamical model. And by doing that, what you're doing is you're trying to create a better tracking algorithm, right? So as I said earlier here, in this method, we are making use of the Kalman filter, right? So in the previous algorithm, when we were looking for the matching or the detection, what we do is we are basically taking different patches between successive frames, and we are trying to match the different patches between frames. Okay, but instead of that, when we are using this particular tracking algorithm, especially when you're using the linear dynamic model with Kalman filter, what you're doing is you're trying to formulate this as a probabilistic problem, okay, or we use probabilistic theory for formulating that particular problem. Okay, so that means this tracking algorithm, whatever is the tracking algorithm we have, that is basically all that we are doing is we are trying to say it is just like finding the probability of the state of an object given the particular observations. Like I can write it this way. I can say the tracking algorithm, okay, that we have here, it is just being reformulated as a probabilistic theory here, where I'm saying I'm trying to find out what is the probability of finding the current state of an object, okay, given the observations over time, right? So here this x basically represents what is the random variable representing the state, and y basically represents what is the random variable representing the observations, okay. And here what we're doing is we're trying to find out p of xy, and this is basically what you call this is the posteriori probability, okay. And the tracking algorithm becomes, as it is reformulated as a probabilistic theory. So what you're trying to find is, as I said earlier, we are trying to find out what is the probability of the state in the current frame with respect to the observations, all the observations that you have made so far. So we'll go to the details in the coming slides. So before that, we'll quickly discuss some basic properties of the probability distributions. Okay. So P of AB basically represents the joint probability, right? So let's say I have P of AB. If I use the conditioning or the factorization principle here, I can write this as P of AB, the joint probability of A and B can be represented as P of A given B into PB, or it can also be written as P of B given A into P of A. Okay. So the next rule is the bias rule, where I can write P of A given B. Okay, can be represented as P of B given A into PA by P of B. So here what this means is, now let's say I have this particular probability, and let's say I want to again frame the problem in such a way that I instead want to use P of B given A instead. So in that case I can make use of the bias rule to just change it to this form and use this. Okay, so this is one formula that you need to remember. Now, another formula is the independence formula, where I say that A and B, they are independent only if and only if I can write P of AB. The joint probability between A and B can be written as P of A into P of B. That is the independence property. And the next property is the marginalization, where I can say P of B can be written as P of AB, the joint probability, integrated over A. Okay, or if I'm taking a summation, I can say it is a summation of all A here. Okay, so these four properties is something that you need to remember, and something that will be useful in the later slides also. Okay, so here when you're trying to do a tracking problem with the help of dynamic models, there are two important cases, or two situations that we may have. One is where you have the dynamics which are linear. So as I said, dynamics is the information on how the object, or what is the state of the object changing over a period of time. Right. So that is a dynamic model. Now this change over a period of time may be linear. Okay. That is one case. Another case would be a non-linear dynamics. Right. So here we won't be studying about this non-linear dynamics case. We will be studying only the case where the dynamics is linear. Okay. So that's why it's called as a tracking with linear dynamic models with Kalman filter. We'll be considering the case of only the linear dynamics. That is, the change over a period of time is linear. Okay, and here, as I said, again, the goal here is, so let's say I have a probability. This is how I represent that. So let's say I have X represented by the state of the object, and here Y is represented by the observations. So what I'm trying to do is I'm trying to find out what is the probability of the change of the state, right, given a linear dynamic model here. Okay, so that is how you can define the particular objective of this particular tracking algorithm. Okay, So what's the time now? I'll just take for 5 more minutes. Now, so here, as I said again, what we are trying to do is trying to find out the probability, right? So instead of finding the probability directly, you can also try to find the probability with respect to the representation, an accurate representation of the posterior probability of the object position given the measurements. So we'll see how that is done. So before we discuss those in details, we'll have to just see this representation of the random variables. So if I represent, let's say, the state of an object given by capital Xi, then what that means is this is the state of the object at the ith frame, right? So it's a random variable which represents the state of the object in the ith frame. But if I use, let's say, a small letter x, right, that denotes what is the value it represents, this particular. So if I write, let's say, if I write it as xi is equal to small x here, what this means is this small x is the value which this random variable or the vector x takes with respect to, or takes for the ith frame. Okay, so x is basically the value here, and x is the random variable that represents the state of the object, and I is basically what is the number of which frame it is. Same way here, capital Y can be used to represent the observations, right? If I write it as P of X condition or given Y. So this capital YI represents what is the observations which are obtained in the ith frame. And if I write a small yi, that is, if I write it this way, what that means is this yi represents what is the value of the particular measurement. Okay, so just take care of these notations of using capital. If I'm using capital letters, it represents the random variables of the either the state or the observation, and the small letters will always represent what is the values which it assumes. Okay, and in while you're doing the tracking, how we can represent this is I can represent this is this way. That is, I can write p of, instead of writing p of x given y, this y can be assumed over all the observations that you have taken so far. So I can write p of xk given y naught to yk. What that means is, I can find the probability of the state of the object in the kth frame, okay, given all the observations that I have made from the 0th frame till the kth frame. That means I can take all the past observations or measurements along with the measurement of the present frame also. I can consider all these past and present observations together in order to find what is the probability of the state in the current frame. Okay, so this is just another expression for representing this, but all that we are saying is that we are taking all the observations, and this is also called as this type of tracking. You can also call it as filtering. We are calling it as filtering because we are using the Kalman filter over here, right? Or another term that we use here is state estimation. Basically, because what we are trying to do is we are trying to estimate what is the state of the object, right? So the term that we can use here is either state estimation, or it is also called as filtering. Okay, and basically what it is doing is the tracking here. Okay, so we can continue we can continue from the next class. Now if you have any doubts, you can ask now. Okay, if you have no doubts, then I'll launch the quiz now. So I'll just launch the quiz within 2 or 3 minutes, and please ensure that you submit the quiz